Look up at the sky on a clear day, and you will see the engine of our solar system, a seemingly eternal sphere of blinding plasma that has nurtured life on our planet for over 4 billion years. However, this celestial guardian is not infinite, and its lifespan is governed by the strict, unforgiving laws of stellar physics. We are going to embark on a chronological journey through deep time, exploring the precise, scientifically verified sequence of events that will lead to the death of our star and the ultimate destruction of Earth. To understand the end, we must first understand the present state of our sun. Right now, our star is in the prime of its life, a phase known as the main sequence. Deep within its core, temperatures reach a staggering 15 million degrees Celsius, or 27 million degrees Fahrenheit. At these extreme temperatures, and under crushing pressures of 265 billion bar hydrogen atoms are forced together in a process called nuclear fusion. Specifically, the sun relies on the proton-proton chain reaction, converting roughly 600 million metric tons, or 660 million short tons, of hydrogen into helium every single second. This violent nuclear furnace produces an outward pressure that perfectly balances the immense inward pull of the sun's own gravity. This delicate state of balance is known as hydrostatic equilibrium, and it is the only reason our star does not collapse in on itself. The energy generated in the core takes over 100,000 years to travel through the dense radiative zone before moving through the convective zone and finally radiating out into the vacuum of space from the photosphere. This steady output of energy bathes the Earth in a habitable glow, maintaining our oceans, driving our weather systems, and powering the complex web of biology. But this golden age is temporary. The sun has a finite supply of hydrogen fuel in its core, and as this fuel is consumed, the chemical composition of the star fundamentally changes. The accumulation of helium ash in the core increases its density, forcing the core to contract slightly, which in turn increases the temperature and the rate of fusion. This means the sun is slowly, but inevitably, getting brighter. This gradual increase in solar luminosity spells doom for our planet, long before the sun ever physically expands. In approximately 1 billion years, the sun will be roughly 10% brighter than it is today. This might sound like a minor increase, but it will trigger a catastrophic chain reaction on Earth. As the solar radiation intensifies, the global temperature of our planet will begin to rise steadily. The first major casualty of this warming will be the silicate weathering cycle, a crucial geological process that acts as Earth's long-term thermostat. As temperatures rise, the weathering of silicate rocks will accelerate, drawing carbon dioxide out of the atmosphere and trapping it in the Earth's crust. Eventually, carbon dioxide levels will drop so low that photosynthesis will become impossible for most plant life. The foundation of the global food chain will collapse, leading to a mass extinction event that will wipe out nearly all complex terrestrial life. But the true horror begins as the oceans start to evaporate at an accelerated rate. Water vapor is a potent greenhouse gas, and as more of it enters the atmosphere, it will trap even more heat, creating a runaway greenhouse effect. The surface temperature will soar, causing even more water to evaporate. The Earth's stratosphere, currently dry and cold, will become saturated with water vapor. High in the upper atmosphere, intense ultraviolet radiation from the brightening sun will bombard these water molecules, splitting them into oxygen and hydrogen. Because hydrogen is the lightest element, it will easily achieve escape velocity and bleed away into the vacuum of space. This process, known as atmospheric stripping, will permanently rob the Earth of its water. Within 2 to 3 billion years, the magnificent oceans that currently cover 71% of our world will be completely gone, leaving behind a vast arid wasteland of salt flats and scorched rock. Without the lubricating effect of water in the crust, the massive tectonic plates that shape our continents will grind to a halt. Earth will become a stagnant, dead world, much like our neighbor Venus, baking under a relentless, increasingly hostile sun. As we move 4 billion years into the future, the Earth is an unrecognizable, barren rock, but the sun is just preparing for its most dramatic transformation. Deep inside the solar core, the last remnants of hydrogen fuel are finally exhausted. The nuclear engine that has sustained the star for 10 billion years suddenly sputters and dies. Without the outward pressure of hydrogen fusion to counteract gravity, the core begins to collapse under its own immense weight. This rapid compression causes the temperature within the core to skyrocket, eventually reaching a terrifying 100 million degrees Celsius, or 180 million degrees Fahrenheit. While the core itself is now composed entirely of inert helium, the layer of gas immediately surrounding the core still contains unburned hydrogen. The intense heat radiating from the collapsing core ignites this outer shell, initiating a phase known as hydrogen shell burning. This new source of energy is far more intense and erratic than the steady core fusion of the past. The massive outpouring of energy from the burning shell pushes against the outer layers of the sun, forcing them to expand outward into space. The sun has now left the main sequence and entered the subgiant phase. As the outer layers expand, they spread the star's energy over a much larger surface area, causing the surface temperature to drop. The sun's color shifts from a brilliant yellow to a deep, ominous red. Over the next billion years, the sun will continue to swell, transitioning into a true red giant. Its luminosity will increase to over 2,000 times its current output, and its physical size will become monstrous. The solar radius will expand to over 140 million kilometers, or 87 million miles. To put this terrifying scale into perspective, the sun will grow so large that it will completely engulf the orbits of the inner planets. Mercury, the closest planet to the sun, will be the first to fall. As the solar atmosphere expands past Mercury's orbit, the intense drag from the stellar gas will cause the planet's orbit to decay rapidly. Mercury will spiral inward, plunging into the fiery depths of the red giant, where it will be instantly vaporized and assimilated into the star. Following the destruction of Mercury, the expanding solar atmosphere will set its sights on Venus. Venus orbits at a distance of roughly 108 million kilometers, or 67 million miles, from the sun, placing it squarely within the projected expansion zone of the red giant. As the outer layers of the sun reach Venus, the planet will experience unimaginable tidal forces and atmospheric drag. The thick, toxic atmosphere of Venus will be stripped away in a matter of days, and the rocky mantle will begin to melt under the extreme heat. Just like Mercury, Venus will be dragged inward by the friction of the solar envelope, spiraling down into the stellar interior until it is completely destroyed. Now, the expanding edge of the sun looms ominously close to Earth. The fate of our planet during this phase is a subject of intense study using 2026 planetary dynamics models. As the sun expands, it also loses a massive amount of mass through incredibly powerful solar winds. These stellar winds will blast away up to 30% of the sun's total mass. Because the sun's gravitational pull is weakening due to this mass loss, the orbits of the remaining planets, including Earth, will naturally expand outward. Earth's orbit could potentially migrate from its current distance of 150 million kilometers, or 93 million miles, out to a distance of roughly 180 million kilometers, or 111 million miles. This outward migration might seem like a saving grace, a chance for Earth to narrowly escape the fiery boundary of the red giant. However, the physics of stellar engulfment are complex. As the sun's outer atmosphere becomes incredibly diffuse, it creates a massive envelope of hot gas that extends far beyond the visible surface of the star. Even if Earth's orbit expands, it will likely still be caught within this tenuous outer atmosphere. The friction generated by Earth plowing through this solar gas will create a drag effect, counteracting the outward migration. This tidal drag will slowly sap Earth's orbital energy, causing our planet to spiral back inward toward the encroaching solar surface. The battle between mass loss, expansion, and tidal drag will determine the ultimate physical survival of our world. Even if Earth manages to maintain a stable orbit just outside the physical boundary of the red giant, the conditions on the surface will be apocalyptic. The sheer proximity of the massive, pulsating star will heat the Earth's surface to temperatures exceeding 2,000 degrees Celsius, or 3,600 degrees Fahrenheit. At these extreme temperatures, the very rocks that make up the Earth's crust will begin to melt. The entire surface of our planet will be transformed into a churning, glowing ocean of liquid magma. Any remaining traces of our civilization, every mountain range, every deep ocean trench, will be completely erased, melted down into a uniform sphere of glowing slag. The intense solar wind, now a raging torrent of high-energy particles, will continuously bombard the planet. Earth's magnetic field, which once protected us from cosmic radiation, will have long since collapsed as the planet's internal dynamo ceased functioning. Without this magnetic shield, the solar wind will directly impact the magma ocean, stripping away any heavy gases that might have outgassed from the melting rock. Earth will be reduced to a scorched, airless husk, a dead cinder orbiting a dying star. Meanwhile, deep within the sun, another catastrophic event is brewing. The core, composed of dense, inert helium, has been continuously contracting and heating up for millions of years. The pressure is so immense that the electrons within the core become quantum mechanically degenerate, meaning they are packed as tightly as the laws of physics allow. This electron degeneracy pressure is the only thing preventing the core from collapsing into a black hole. Finally, when the core temperature reaches a critical threshold of 100 million degrees Celsius, or 180 million degrees Fahrenheit, the helium atoms begin to fuse together in a process called the triple alpha process. Because the core is supported by degeneracy pressure rather than thermal pressure, the sudden onset of helium fusion does not cause the core to expand and cool. Instead, the temperature skyrockets, causing the fusion rate to increase exponentially. This results in a runaway nuclear explosion known as the helium flash. The helium flash is an event of unimaginable violence. In a matter of minutes, the core of the sun generates a burst of energy equivalent to the combined output of an entire galaxy. However, this massive explosion is entirely contained deep within the star. The energy is absorbed by the surrounding layers of gas, and incredibly, no visible change is immediately apparent on the surface of the red giant. The primary effect of the helium flash is to finally break the quantum degeneracy of the core. The sudden influx of thermal energy causes the core to expand rapidly, which in turn lowers the temperature and stabilizes the helium fusion process. The sun now enters a new phase of its life, known as the horizontal branch. During this phase, the sun will actually shrink in size, and its surface temperature will increase slightly, shifting its color from red to a yellowish orange. For roughly 100 million years, the sun will enjoy a brief period of stability, peacefully fusing helium into carbon and oxygen in its core, while a shell of hydrogen continues to burn above it. If Earth survived the initial red giant expansion, it will now orbit a slightly smaller, but still incredibly hostile star. The magma ocean on Earth's surface might cool slightly, forming a thin, fragile crust of dark basalt. But this respite is only temporary. The helium fuel in the core is highly inefficient compared to hydrogen, and it will be exhausted in a cosmic blink of an eye. When the core runs out of helium, the sun will face its final fatal crisis. The core, now composed of inert carbon and oxygen, will contract once again under the crushing force of gravity. The temperature will rise, but the sun simply does not have enough mass to generate the immense heat required to fuse carbon. The core is dead, and the star's nuclear engine has permanently shut down. However, the layers of gas surrounding the core are still highly reactive. A shell of helium begins to fuse intensely, surrounded by an outer shell of fusing hydrogen. The sun has entered the asymptotic giant branch, or AGB phase, and its final death throes have begun. The asymptotic giant branch phase is characterized by extreme instability. The dual shell burning of hydrogen and helium is highly sensitive to temperature changes, leading to massive thermal pulses. Every 100,000 years or so, the helium shell will experience a runaway fusion event, sending a massive shockwave of energy outward through the star. These thermal pulses will cause the sun to expand and contract violently, pulsating like a dying heart. With each pulse, the sun will swell to an even greater size than its first red giant phase, potentially reaching a radius of 150 million kilometers or 93 million miles. If Earth managed to survive the first expansion, it will face an even greater threat now. The thermal pulses will generate incredibly powerful stellar winds, far stronger than anything the sun has produced before. These winds will literally tear the outer layers of the sun away, ejecting massive amounts of stellar material into deep space. The sun will lose up to half of its total mass during this violent phase. As the sun sheds its mass, its gravitational grip on the solar system will weaken dramatically. The orbits of the surviving planets, including Mars, Jupiter, and Saturn, will expand significantly. If Earth is still intact, its orbit will also push outward, potentially saving it from final engulfment. However, the intense radiation and stellar winds will continue to blast the charred remains of our planet. The material ejected by the dying sun will form a vast, expanding cloud of gas and dust known as a planetary nebula. This beautiful, glowing shroud will encompass the entire inner solar system, illuminated by the intense ultraviolet radiation from the exposed, superheated core of the sun. The planetary nebula will be a spectacular sight from afar, a glowing monument to the star that once nurtured life. But from the perspective of the inner solar system, it is a violent, chaotic storm of superheated plasma and heavy elements. The carbon and oxygen forged in the dying star's core will be seeded into the interstellar medium, eventually becoming the building blocks for new stars, new planets, and perhaps new life in the distant future. As the planetary nebula expands and dissipates into the interstellar void over tens of thousands of years, the true corpse of our sun will finally be revealed. Stripped of its outer layers, all that remains is the incredibly dense, superheated core, a stellar remnant known as a white dwarf. This dead star will be roughly the size of Earth, measuring about 12,000 kilometers or 7,500 miles in diameter, but it will contain roughly half the mass of the original sun. This means the density of the white dwarf will be incomprehensible. A single teaspoon of white dwarf material would weigh over 5 metric tons, or 5.5 short tons, on Earth. The gravity on the surface of this dead star will be hundreds of thousands of times stronger than Earth's gravity. The white dwarf will initially be incredibly hot, with surface temperatures exceeding 100,000 degrees Celsius, or 180,000 degrees Fahrenheit. It will emit a harsh, blinding white light, composed mostly of intense ultraviolet radiation. If Earth survived the red giant and AGB phases, it will now find itself orbiting this tiny, brilliant point of light in the freezing darkness of space. The distance between Earth and the white dwarf will have increased significantly due to the sun's mass loss, meaning the amount of energy reaching our ruined planet will be a tiny fraction of what it receives today. The magma ocean that once covered Earth will rapidly cool and solidify, plunging the planet into a deep, eternal freeze. The surface temperature will plummet to hundreds of degrees below zero. Earth will become a dark, frozen tomb, a silent monument to the vibrant biosphere that existed billions of years prior. The sky above this dead world will be pitch black, dominated by the piercing, cold light of the white dwarf and the distant, unchanging stars. There will be no atmosphere to scatter the light, no weather, no sound, and absolutely no possibility of life. The solar system, once a dynamic and complex clockwork of planets and moons, will be reduced to a graveyard of frozen rocks orbiting a cooling ember. The physics governing the white dwarf are entirely different from the nuclear fusion that powered the main sequence sun. The white dwarf generates absolutely no new energy. It is essentially a glowing ember, slowly radiating its residual heat away into the absolute zero vacuum of space. This cooling process is incredibly slow, dictated by the laws of thermodynamics and the extreme density of the star. Because the white dwarf is supported by electron degeneracy pressure, it cannot contract any further to generate heat. It is locked in its current size, a perfect sphere of crystallized carbon and oxygen. Over the next several billion years, the white dwarf will slowly transition through the color spectrum as it cools. It will shift from a blinding white to a pale yellow, then to a deep orange, and finally to a dim, glowing red. As the temperature drops, the interior of the white dwarf will undergo a bizarre phase transition. The immense pressure will force the carbon and oxygen atoms to arrange themselves into a rigid, crystalline lattice. The core of the dead sun will literally transform into a massive cosmic diamond suspended in the void. This crystallization process releases a small amount of latent heat, which temporarily slows down the cooling rate. But it is only a minor delay in the inevitable march toward absolute zero. The surviving planets, including the frozen husk of Earth, will continue their silent orbits around this cooling diamond. The orbital dynamics of this dead solar system will be incredibly stable, as there is no longer any solar, wind, or atmospheric drag to perturb the planets. Earth could theoretically orbit the white dwarf for trillions of years, completely undisturbed by the passage of time. However, the universe is a dynamic place, and over such immense timescales, even the most stable systems can be disrupted. Close encounters with passing stars or rogue planets could gravitationally scatter the remaining planets, potentially ejecting Earth from the solar system entirely, sending it drifting into the cold, dark expanse of interstellar space as a rogue planet. If Earth manages to avoid being ejected from the dead solar system, it will bear witness to the final, ultimate fate of our star. After tens of billions, perhaps even hundreds of billions of years, the white dwarf will have radiated away the last of its residual heat. Its temperature will drop to match the ambient background temperature of the universe, just a few degrees above absolute zero. At this point, the star will cease to emit any visible light or heat. It will become a black dwarf, a completely dark, invisible object drifting through the cosmos. The universe is currently not old enough for any black dwarfs to exist, making them a purely theoretical yet mathematically certain endpoint of stellar evolution. When our sun finally becomes a black dwarf, the solar system will be plunged into absolute eternal darkness. The frozen remains of Earth will orbit an invisible mass, detectable only by its gravitational pull. The story of our star, which began with the collapse of a vibrant nebula and burned brightly for 10 billion years, will end in cold, silent obscurity. This chronological journey through the death of the sun highlights the incredible power and the inevitable mortality of the celestial bodies that govern our universe. The destruction of Earth is not a matter of speculation, but a certainty dictated by the fundamental laws of physics and thermodynamics. The 2026 Helioseismology data and planetary dynamics models provide us with a precise, terrifyingly clear picture of our planet's final moments. From the boiling of the oceans to the melting of the crust and the final, silent orbit around a dead star, the fate of Earth is inextricably linked to the life cycle of the sun. While this future is billions of years away, understanding it gives us a profound appreciation for the delicate, temporary balance that allows life to exist on our pale blue dot. We are living in a narrow window of cosmic time, a brief golden age where the conditions are just right for liquid water, complex chemistry, and conscious observers to marvel at the mechanics of the universe. To fully grasp the magnitude of this stellar evolution, we must delve deeper into the specific mechanics of the mass loss that occurs during the red giant and asymptotic giant branch phases. The solar wind, which currently flows outward at a relatively steady rate, will become a violent, chaotic storm. As the sun's outer layers expand and cool, the gas becomes less transparent to the radiation pushing up from the interior. This opacity traps the radiation, creating immense outward pressure that literally blows the outer layers of the star into space. This process is not smooth or continuous. It happens in massive, episodic ejections, driven by the thermal pulses deep within the helium and hydrogen burning shells. Each pulse sends a shockwave through the star, lifting millions of tons of material off the surface and accelerating it to escape velocity. The composition of this ejected material is crucial to the chemical evolution of the galaxy. The sun will not just be ejecting unburned hydrogen and helium. The intense convection currents within the red giant will dredge up heavy elements forged in the core, such as carbon, nitrogen, and oxygen, and transport them to the surface. These elements will then be blown out into space by the stellar winds. This process, known as the third Dredge-Up, is responsible for seeding the interstellar medium with the building blocks of life. The carbon in our bodies, the oxygen we breathe, and the nitrogen in our atmosphere were all forged in the hearts of dying stars and ejected into space in exactly this manner. Our sun, in its death throes, will contribute to this cosmic recycling program, providing the raw materials for future generations of stars and planets. The expanding planetary nebula will be a rich chemical soup, containing complex molecules and dust grains that will eventually coalesce into new worlds. So, while the death of the sun means the absolute destruction of Earth, it is also a necessary step in the ongoing evolution of the universe. The precise timing of these events is calculated using advanced stellar evolution models, calibrated with the latest observational data from the European Space Agency's Solar Orbiter and NASA's Parker Solar Probe. These instruments have provided unprecedented insights into the behavior of the solar wind and the internal structure of the sun. By measuring the acoustic waves traveling through the sun, a technique known as helioseismology, scientists can map the density and temperature of the solar interior with incredible accuracy. This data confirms that the sun's core is slowly contracting and heating up, exactly as predicted by theoretical models. The timeline is set. In 1 billion years, the oceans boil. In 5 billion years, the core hydrogen is exhausted. In 7 billion years, the sun reaches its maximum size as a red giant, engulfing the inner planets. The exact fate of Earth remains the only slight variable, dependent on the precise balance between solar mass loss and tidal drag. But whether Earth is vaporized within the stellar envelope, or left as a scorched cinder orbiting a white dwarf, the biosphere is doomed. This knowledge forces us to confront the long-term future of humanity. If our species, or whatever we evolve into, hopes to survive the death of our star, we must eventually leave this solar system. We must master interstellar travel and find a new home around a younger, more stable star. The death of the sun is the ultimate ticking clock, a cosmic deadline that demands we expand our horizons beyond the confines of our local neighborhood. The physics of stellar death are inescapable, but they also provide a roadmap for our survival. By understanding the mechanics of the universe, we can anticipate its dangers and adapt to its changing conditions. The story of the sun's death is not just a tale of destruction, but a testament to the power of scientific inquiry and the resilience of the human spirit in the face of cosmic inevitability. As we conclude this detailed examination of Earth's final moments, let us review the stark, undeniable facts. The sun, a massive sphere of fusing plasma, is bound by the laws of thermodynamics to eventually exhaust its fuel. The resulting expansion into a red giant will increase its radius to 140 million kilometers, or 87 million miles, obliterating Mercury and Venus. Earth will be subjected to temperatures exceeding 2,000 degrees Celsius, or 3,600 degrees Fahrenheit, melting its crust and stripping its atmosphere. The subsequent helium flash and thermal pulses will violently eject the sun's outer layers, forming a planetary nebula and leaving behind a dense, crystalline white dwarf. This dead star, roughly 12,000 kilometers, or 7,500 miles in diameter, will slowly cool over trillions of years until it becomes a dark, invisible black dwarf. The frozen, charred remains of Earth, if not completely vaporized, will orbit this dark mass in eternal silence. This is the scientifically verified future of our solar system, based on the most rigorous 2026 astronomical data. It is a future devoid of life, but rich in complex physics and cosmic beauty. The destruction of our world is a necessary component of the galactic life cycle, a violent redistribution of matter that paves the way for new creation. We are privileged to exist in this brief window of stability, equipped with the intellect to understand our place in the universe and the ultimate fate of our home. The stars above us are not eternal, and neither is the ground beneath our feet. But the knowledge we gather, the understanding we build, and the legacy we leave behind can echo through the cosmos long after our star has faded into the dark. Thank you for joining us on this journey through deep time. Keep looking up, keep questioning, and never stop exploring the magnificent, terrifying mechanics of the universe. The legacy of our solar system will not be one of permanent destruction, but of transformation. The heavy elements forged in the dying heart of our sun, the carbon, the oxygen, the nitrogen, will drift through the interstellar medium for millions of years. Eventually, these elements will encounter a massive cloud of cold molecular gas. The gravitational perturbation from a passing star, or perhaps the shock wave from another distant supernova, will cause this gas cloud to collapse. As it collapses, it will spin faster and heat up, forming a new protostar at its center. Surrounding this new star will be a protoplanetary disk, a swirling mass of gas and dust enriched by the ashes of our dead sun. Within this disk, dust grains will collide and stick together, forming pebbles, then boulders, and eventually new planets. Some of these planets may form in the habitable zone of their new star. They may have rocky surfaces, liquid water oceans, and thick atmospheres. And within those oceans, the complex organic molecules forged in the death throes of our sun may once again combine to form the spark of life. This is the grand, cyclical nature of the cosmos. The death of one star is the birth of another. The destruction of Earth is simply the dismantling of a temporary structure, returning its building blocks to the universe so that something new can be created. While the specific arrangement of atoms that we call Earth will be gone forever, the fundamental components of our world will endure. They will become part of new landscapes, new atmospheres, and perhaps new living beings who will look up at their own star and wonder about its ultimate fate. The story of the universe is a story of continuous change, a relentless march of thermodynamics and gravity that creates, destroys, and recreates in an endless, beautiful cycle. We are a part of that cycle, a brief, conscious manifestation of the cosmos, observing its own magnificent mechanics. Thank you so much for watching. Please subscribe and help me get to that 1,000 subscriber milestone.